recording. So let's see, today's topic is Heap, right? Okay, so let's see what is Heap. So we make like the session not long like the other session. I will try to focus only on the important stuff to know, and there's a couple videos we're gonna watch that will make this topic more clear for us before we jump to the let's code problem. Let's aim to like solve these bots. They are like bots, very interesting. So a heap is a specialized tree-based data structure which is a complete tree that satisfies the heap property, max heap and min heap. Let me read it from here because there's more details. I will share the link. So a heap is a special tree-based data structure that satisfies the heap property. It's a complete binary tree, which means all levels of the tree are fully except possibly for the last level, which is filled from the left to right. So it is a binary tree, and that is have all level fully filled. Only the last one, it's okay if it's not fully filled. There are two types of heaps, max heap and min heap. It's gonna be more clear when we're gonna jump to the video. The main operation or on a heap are insertion when a new element inserted into the heap, deletion when the root element is removed from the heap, pick the operation return the root heap. Now in Python there is a model that do this for us. We don't need to implement this algorithm from scratch. We can just use heap queue. So this heap queue will do like it's the same way we did use the queue. It's the same, and we're gonna see this in details. So far we just have idea about what is heap. So the heap is okay, so a lot of people join. Maybe I should start again. so far we're just reading what is heap. So heap is a special tree-based data structure that satisfies the heap property. It is a complete binary tree, which means all levels of the tree are fully filled except possibly for the last level. So a complete binary tree is a heap, and this heap can be two types, either max heap or min heap. Max heap, for any given node, the value of, let's say, node 1, the value of 1 is greater than or equal the value of children. So this means max heap. The min heap is for any given node, the value of for example node 1 is less, or like the roots is less than or equal to the value of its children, which means min heap. Now let's make this clear with this video. It will make us understand the heap. Okay, so this part is important in the context of algorithm interview, heaps and prior to queue. So we need to understand what is prior to queue, and then we can understand heaps, then we're gonna solve the problems. Can be treated as same data structure. A heap is useful data structure when it is necessary to repeatedly remove the object with the highest or lowest priority, or when insertion need to be entered. What this mean?
Interspersed
with removal of the root node. other part is important here, and this is all gonna make sense after we watch this 4 video. So there's a technique, a mention of k. If you see a top or lowest k being mentioned in the question, it's usually a signal that a heap can be used to solve the problem, such as top k frequent element. If you require the top k element, use a min heap of size k. Iterate each element pushing it into the heap. For Python, use heap q. Invert the value before pushing to find the max. Whenever the heap size exceeds k, remove the minimum elements. That will guarantee that you have the k largest in. Okay, this is gibberish, we'll not understand now, but after we do watch this video, it's gonna be more clear. Okay, so the first video is, let's understand priority queue. Okay, let me share screen.
Code. Along with all the priority queue stuff, we're also going to talk about heaps, since both topics are closely related, although not the same. So the outline for the priority queue series is, we're going to start with the basics, talking about what are priority queues and why they're useful. Then we'll move on to some common operations we do on priority queues, and also discuss how we can turn min priority queues into max priority queues, followed by some complexity analysis. Then we'll talk about common ways we implement priority queues. Most people think heaps are the only way we can implement a priority queue, or that priority queues somehow are heaps. I want to dispel that confusion. Next, we're going to go into some great detail about how to implement the priority queue using a binary heap. There we'll look at methods of sinking and swimming nodes up and down our heap. These terms are used to, again, shuffle around elements in a binary heap. As part of the implementation explanation, I'll also go over how to pull and add elements. So there's a lot to cover, so let's get started. Discussion and examples. This is going to be part 1 of 5 in the priority queue series. So what is a priority queue? A priority queue is an abstract data type that operates similar to a normal queue, except for the fact that every element has a certain priority. So elements with a higher priority come out of the priority queue first. As a side note, I'd like to remark that priority queues only support elements that are comparable, meaning that the data we insert into the priority queue must be ordered in some way, either from least to greatest or greatest to least. This is so we can assign relative priorities between elements. Okay, let's go into an example. So suppose we have all these values that we insert into our priority queue on the right, and that we impose an ordering on the numbers such that we want to order them from least to greatest. So the smaller numbers have a higher priority than the bigger ones. So they will be removed from the priority queue first. Now, suppose we have now a list of instructions. So what the pull operation means is remove the element that has the highest priority in our priority queue. So let's see how this works. So if I say pull, then I remove the element with the highest priority, which happened to be 1. Now I say add 2, so we add 2 to our priority queue, and pull, so next we pull the smallest element in our priority queue, and that happened to be the 2 we just added. Next we add 4, pull the smallest, this is 3, add 5, also add 9, and then pull the rest. So as I pull the rest, I'm continuously grabbing the smallest element in the priority queue. So it turns out that as we added and pulled numbers, we got an ordered sequence. This is a coincidence, actually. As we add and pull numbers from the priority queue, we do not necessarily end up getting an ordered sequence. We are only guaranteed that the next number that is removed from the priority queue is the smallest number that was currently in the priority queue. So how does the priority queue know which is the next smallest number to remove? As humans, we could see the numbers visually inside the priority queue and look and know what one was the smallest the pull operation was going to return. But fundamentally, how does the machine know this? Does it resort all the elements inside the priority queue before each pull operation? No, in fact, that would be highly ineffective. Instead, it uses what is called a heap.
Okay, finally the heap mention. So this is prior to queue, and behind the scene it's using heap. So we can have this like random data, and but we want to like when we pull either like the lowest element or like the max element. Let's see, let's keep going.
The next big question then is the next heap. So the next big question then is, what is a heap? Usually I make up my own definitions, but I really like this one from Wiki. A heap is a tree-based data structure that satisfies the heap invariant, also called the heap property. If A is a parent node of B, then A is ordered with respect to B for all nodes A and B in the heap. What this means is the value of the parent node is always greater than or equal to the value of the child node for all nodes, or the other way around, that the value of the parent node is less than or equal to the value of the child node for all nodes.
Okay, so this in the max heap, the root is always gonna be greater, or like the parent is always greater than children. But in main heap, the parent is always less than the children.
This means we end up getting two types of heaps: max heaps and min heaps. So max heaps are the one with where the parent node is always greater than its children, and the min heap is the opposite. So both of the following are actually binary heaps. Binary because every node has exactly two children, and the children you cannot see are null values I have not drawn in. So why are we interested in heaps? Well, heaps form the canonical underlying data structure for priority queues. So much so that priority queues are sometimes called heaps, although this isn't technically correct, since the priority queue again is an abstract data type, meaning it can be implemented with other data structures also. Okay, we're going to play a little game. I'm going to give you some structures, and you need to tell me whether it is a heap or not.
Oh, okay. Who is ready to play?
Sure.
Okay, let's
Yes,
type,
it's a heap.
let's type in the chat
Oh,
yes
that's
or
not a
no.
heap.
It is a heap.
Because every root has two children. I don't know if that's
I
correct.
think that's not a heap.
Okay, yeah. It's not a heap. It's not a heap because the
Hmm.
8 has more than one. Yeah, it's true. More than one children. So
Okay.
No, that's
let
not the
me-
reason. The reason is because if you check, right, it's almost like a balanced tree. It gets created in order. So you start from the left, right? So the root has a left and a right, and then the children of the root have a left and a right each. But if you go down to the third level, you'll check that 3 has something on the very left, but on the very right as well, there's something. That shouldn't have been the case. The next node that should have been filled is the one adjacent to the 3. So it would be that one in the very left corner that should have the next few children, I believe.
Okay.
I was also thinking if it's 2 and 3 because they don't have any child. So I don't know. Maybe.
Okay, so someone said yes, it's heap. No, that not a heap, not a structure heap. It's not a heap because it's not a complete tree, I guess. Yeah, maybe. I actually don't know. I think it's a heap because this is a tree. This is a complete tree, right? Each level
It's
is
not
full.
really-
But level 3, it is
Yeah,
like a different. Yeah, it
I
is
think
three.
I think the last level is okay to be not full, but each level here is full.
Oh, okay.
Okay, but 3 is
Sorry.
greater than 2 in the last level.
Okay, I think we read it somewhere here. Can you see my screen? You can see my screen, right?
Yes, boss. Yes, boss.
Okay, a heap is a special tree-based data structure that satisfies the heap property. Okay, we need to know what is the heap property. It is complete binary tree, which means all levels of the tree are fully filled except possibly for the last level, which is filled from the left to right. So last level, it's okay to not be fully filled. This one is
No.
filled, this one is filled.
Remember what it says there? It says it's filled from the left to the right?
Please, can we watch this to know if it's correct or not, please? Because
Okay.
I'm curious. I'm really
Yes.
curious.
Okay, let's see. So I'm saying it is what's it called? I'm saying it is a heap, right? Okay, let's see.
So inspect the following structure and try to determine whether it's a heap or not. You can pause the video if you like, but I'm just going to give you a short moment here.
Okay. No, we have. Please mute your mic. Francis, please mute your mic. Okay, so he said no.
No, we have a violation of the heap invariant in this tree, so it's not a heap.
Okay. So we didn't focus on the value. We focus only in this the design.
3 is greater than 2.
Okay. So here the parents is 2 and the child is 3, which doesn't make sense in this case. Okay, let's go. Is there more?
Is this structure a heap?
What the hell?
Hell no.
Hell no, yeah. It's not a binary tree. Yeah,
I don't think this is a heap. Or we are missing something.
Can it be a mean heap or already heap?
It's not
Yeah,
a because
I believe a heap should have it is a binary tree that has the root has 2 children, right? But this one I don't know. I'm not seeing 2 children here, so
Yeah.
I don't think it's
I think the parent is the one with the 0 number. So it has 3 children. So it's not a binary tree at all.
Yeah.
It's a trinary tree. Trinary tree, yes.
Wait, so
Even if it was a heap, there's also a heap invariant there, 2, 3. No, it's okay. It's not
No,
a
it
heap.
would be a min heap in that case. If it wasn't for the fact that there were 3 branches there, it would be a min.
I think it's a min heap.
It can be a min heap because there are 3
Sorry,
in the first after the root.
I want to ask a question. Sorry, please.
yes.
Are you so a parent can have just one child and it can still be a heap, right? I just want to clarify that so that we know where we are.
Well, it depends on the
Can you
the
repeat the
level,
question?
right? So if it has just one child, does it have other branches after that child? Maybe the child has like about 4 levels after the child. So if it has something like that, it means it's not a heap because it must be a complete binary tree, meaning that it must fill all the
Exactly.
You're right.
Exactly.
This
That's what I was
level right
trying to
here is empty.
Exactly. So it doesn't
Yeah.
matter about the values. It has to meet the value property and also the structure property as well. So
So
that
the
makes
value
sense.
is correct here, right? 0, 1, 2, 3. But the structure is not. Let's see. Plain. What? Yes? This is a tree and it satisfies the heap invariant. Heap like this are often seen in binomial heaps. Okay, something is
Yes,
wrong
it
there.
That was
is
why I
a
asked
heap.
that question. That can a parent have one child and still be a heap? That's why I asked that question to see.
Okay.
I'm confused now.
Yeah, me too. Something is not. Okay, let's see what he said.
Heap because it satisfies the heap invariant and it is a tree.
Okay, so it should be just a tree. Why here they said complete tree? Okay, because this is not complete tree. Okay, that is the difference, I guess. What? Maybe there's two differences.
They said complete tree,
Yes.
not complete binary tree. Okay, here is the point. So it's not necessarily a binary tree.
Okay, is this a complete tree?
I don't know.
Okay, maybe we'll ask. Is heap have to be complete tree?
And please
No.
also ask what is a binomial heap. Please also ask that question
Yeah,
later.
he did mention it. He did
binomial
mention it
heap.
here.
Yeah.
Yeah, he did mention it. No, a heap does not have to be a complete tree. There are two main type of heap: binary heap and binomial. Oh, okay. So we are studying binary heap. So I probably should say here binary heap. Binary heap. In binary heap, the tree is complete at all level except possibly the last level. Okay, we know that. Binomial. How to read this?
Binomial.
Binomial heap is a type of heap data structure that is a collection of binomial tree. Okay, so there is two type. So we are in good path. We're not confused. We just didn't know this exists. Okay, let's keep going. Yes.
So we often see heaps like these in what are called binomial heaps. Note that heaps aren't necessarily binary heaps. They can have any number of branches. On to our next.
Okay, he did mention that. Oh my god, what the hell is this? Okay. What is this, guys? Hip or not hip? Is this binomial or is there another category we don't know about?
In my professional opinion, I'd say this is definitely a heap. A binomial, I don't know actually.
Personally, I don't think.
Okay, let's see. Is it a binary tree? Is this a binary tree? It is, right? Because this node have two children. This is.
It's not.
How about seven? Seven has 3 children. How is that possible? Can he have 3 children?
Okay.
Seven. He has 3 children. I don't know.
Oh.
3 or 1.
Has 3 children. I think it's 3 that has 3 children.
Okay.
That is 6, 7, 6, and because 6 has 3 children. 6 and 6.
Also, in level 2, 6 have two fathers. Two parents.
Yeah, exactly. They're having more than one root. So I don't know how that happens.
This is really interesting. Let's see. Let's play.
Next one. So is this a valid heap?
No? Yes?
Yeah, it's a valid heap.
What?
Because even though this one is strangely structured, we're free to move around the visual representation of the nodes as we please. So yeah, it's a valid heap.
What?
Okay, I think the structure is not the structure is not well organized. But if you look at it very well, it looks like it looks like a heap because that 7, if you raise it up, if you bring it up, you see it's actually the root of 6 and 7 there. So it's
7.
scattered, but yeah, this 7 there, it looks like the root of 7 and 6. Like if you look at it very well.
So I think it's like a binomial heap. Binomial heap.
No, I think it's binary. I don't know. I think it's binary.
No, it's
You know,
not.
Oh, this is binomial. It's got
I think
some of the
about
nodes
six
have more than
and
2
three
children.
out of
I
Okay,
think the video
okay.
talk about heap on general, not a special kind.
Okay.
Can you play with whether
Yeah,
it's played?
let's play and see if there's more.
How about this one?
Ah, no, that's the devil's tree. Like, not a heap.
Oh, he did. I didn't pause. Okay, what is this? I guess you saw it.
somebody
That's
says
something evil.
Somebody says the devil's tree. Explain.
You see that second level, they share a child there, so that's not that's maybe a graph or something. I don't know, man. That's not a tree.
Okay, let's see.
How about this one? No, this structure is actually not even a tree because it contains the cycles. All heaps must be trees. What about this one?
Oh, okay. What about this one? This is not a tree,
100%.
right? Doesn't have children.
This is a tree. This is a graph.
It's
this
a
is
tree.
everything.
It's a graph. Yes, it can have just one vertex.
It's
Is
a
it-
heap. I think it's a
I
heap.
don't know if it's a heap. I don't know if it's a heap. Anyways, it's a tree.
Okay. Now, maybe this is a binomial tree.
No, this is maybe it's just like the roots.
Yeah, maybe it's a binomial. Maybe. Well, this cannot be binary. Anyways.
Because actually I don't know this. What is the property of the each binomial tree follow the complete, but the heap is not necessary complete binary. So it doesn't need to be complete. So if there is only the roots, probably it's still binomial. Maybe, let's see.
Yeah, it's a heap. What about this one?
Finally.
Not a heap.
Okay, if that one is heap, this must be a heap too.
Yeah, I'm with you. It must be a heap.
Yeah.
Yes. The heap.
It's
Yes.
Also a heap, because it satisfies the heap invariant that all nodes are less than or equal to or greater than or equal to its parent. How about this one? No.
This is no.
The 10 value in the middle. It doesn't make sense.
It doesn't satisfy the invariant. It should have been greater than 10.
So in the root should have children less, and this should be less than this one for like the max heap.
Oh yes. You're right. Sorry.
And the main heap is
It's
way.
not a heap because it does not satisfy the heap invariant. However, if we do change the root to be 10, then we can satisfy the heap invariant via a min heap. Or rather, sorry, a max heap.
I was surprised when he said mean.
surprised for what?
He had interchanged.
No, when he said mean heap, I was surprised. I knew it was a max heap. So yeah.
Yeah. He mixed up the words, I think.
Or rather, sorry.
This is a min heap. I think it's max heap.
Yeah, so he said mean, I think, at the first instance.
Oh wait, let's see. Max heap have the root greater than children. Min heap have less. The root is less. Maybe it's a mistake.
Yeah, he corrected it.
Okay.
Max heap. So when and where is a priority queue and a heap used? Probably one of the most popular places we see priority queues is in Dijkstra's shortest path algorithm to fetch the next nodes we explore. Priority queues are really handy anytime you also need a behavior in which you need to dynamically fetch the next best or the next worst element. They're also used in Huffman encoding, which is often used for lossless data compression. Many best first search algorithms use priority queues in their implementation to continuously, again, grab the next most promising node in the graph as it's being traversed. And finally, we also see priority queues in Prim's minimum spanning tree algorithm on directed graphs. So it seems priority queues are really important, especially for graph theory algorithms, which is where we see them often. Okay.
This part, we don't need to focus on it right now. If someone wanna watch it later, he can. Here's the video. Because we have another 3 video to watch, and we don't wanna make this boring. So this one also gonna make the heap more clear for us. Let's take a look on this video.
Today we're going to learn about heaps. You often hear the word heap when discussing storage for garbage collection in languages such as Java. But this video is about the heap data structure that is used to manage information. Heaps are sometimes called binary heaps and are nearly complete binary trees. Here's an example of a heap. By a nearly complete binary tree, I mean that all levels are filled except the lowest, and the lowest level is filled up to a certain point starting from the left. Uses of heaps include heap sort and priority queues. And there are 2 kinds of heaps, max heaps and min heaps. On the left, we have a max heap. The condition for a max heap is that the value of the node I is less than or equal to the value of its parent. Max heaps are used for heap sort. Similarly, for the min heap, the value of the node I is greater than or equal to the value of its parent. Min heaps are great for priority queues. Because we said heaps are nearly complete binary trees, we know that the height of a heap is big O of log n, which you'll see in various operations that we'll learn later. I'd also like to show heaps represented as an array. Here's our max heap, and here it is as an array.
Oh. Okay, 21, the root, 17, 15, and 14.
Yeah, level by level.
The root of the tree is at index 1 of the array. To get a node's left child, you simply take the index times by 2. And to get the node's right child, you take the index times by 2 and add 1. Finally, to retrieve a node's parent, is the floor of the node's index divided by 2. We choose to put the root at index 1 instead of 0, as it keeps this arithmetic cleaner, and most computers can do these operations with fewer instructions. Let's take a look at 15, which is at index 3. The left child of 15 is equal to 2 times 3, which is the 6th index, and a node value of 12. The right child of 15 is 2 times 3 plus 1, which is the index of 7, or the node 13. Lastly, the parent of 15 is the floor of 3 divided by 2, which is the first index and the root of our tree, 21. You know I prefer brevity, so we'll end the video here, and in the next...
Thank you, sir. let's go to the second video. This is gonna also make it more clear how when we pop, because when we add a new element to the heap, when we pop it, what happens in the heap? How does it sort itself automatically? Let's see.
Today we're going to learn heap sort. Let's start with some terminology. A heap is simply an ordered binary tree. A max heap has a restriction that the value of the parent nodes are greater than the value of the child nodes. Here's an example of a max heap. We'll make use of a few functions when running heap sort. First, we have build max heap. This creates a max heap from an unsorted array. We'll also use heapify. This is similar to build max heap, except faster because we assume part of the array is already sorted. You'll see what I mean. One note, for this video, I'm less concerned with you knowing how these methods work, but rather that they exist and when to use them. Once you understand the basics of heap sort, you'll understand these functions from their pseudocode. Let's get started. We have the following array that we're tasked to sort. In a nutshell, we'll continuously create max heaps to find the largest item. We'll then remove that item from the heap and into a sorted partition. We'll begin by representing our array as a tree.
Okay, so we're gonna convert this array to a tree. The roots H5391. Is this max heap or min heap? It's like an order. And the goal is to make it order. Let's see how that's gonna work.
To see how we did that, simply look at the array from left to right and the tree from top to bottom. Now that we have a tree, let's create our first heap. We assume this is an unsorted array, so we call build max heap.
Okay, we call build max heap function on this array. H return this one. So it's return a max heap 9 H5321. So it did sort it automatically. Max heap.
Now that we have our max heap, we know the largest item, 9. We swap 9 with the item at the end of the array, 1. Finally, we remove 9 from the tree and consider it sorted.
Okay, let me go back. Okay, so this is...
Finally, we remove 9 from the tree and consider it sorted. Looks good so far, except we're back to having a tree and not a heap. This time we call heapify, since only the item 1 is out of place.
Why did this?
We're back to having a tree and 9 from the tree. Swap 9 with the item at the end of the array, 1. Finally,
what? Why I did this? Why I switch them?
know the largest item, 9. We swap 9 with the item at the end of the array, 1.
Okay, he swapped this. Oh, maybe just for example to show us what will happen in case it was just one element not sorted. Let's see.
No, he's trying to sort this.
I think because he's doing a sort, so he's doing the list element. He's putting the list element first, then the largest on the other end of the array.
Oh. Okay, so this is max heap. To sort it, 1 should be here. 2, 3, 5. Okay, I see.
We know the largest item, 9. We swap 9 with the item at the end of the array, 1.
Okay, he did switch this to this. I believe this is pop. When you do pop, it give you the element at the end.
Finally, we remove 9 from the tree and consider it sorted. Looks good so far.
Okay, so it got to remove this one, and then this one become the first, the root. Okay, let's keep going. Maybe
Except we're back to having a tree and not a heap. This time we call heapify, since only the item 1 is out of place. 1 floats down.
So he did use pop. 1 was here. He did use pop. When he did use pop, the roots gets pop, so it gets removed. And because this is a heap, it's gonna sort itself automatically. So 1 become here.
Sorry, I think what he's doing is he's always placing the largest number to the root. So that's what he's doing. So he before in the sense that he has to put it in order. Like looking at 1, 3, 2 now, 3 will still have to come up. Definitely, because it's out of place. 1 is lesser than 3 and 2.
I think what I think he's actually doing is that he's swapping it. Heapify is swapping between
and the largest number
1 and 8.
Exactly. You see now, 3 has come up. So that's what I'm saying. Oh, yeah.
So I think he looks for the highest number between 2 child and then swaps the highest number.
Exactly. He's using the max heap. Yes. Exactly. That's it.
Okay, let's keep going. Maybe it's gonna be more clear. But what's happening here when he uses heapify, it puts this one to this level, then to this level. So 1 become here, and 3 go up. So we can keep the heap property, right? Because 3 should be larger than 1 and 2.
Yes, that's the max heap property. Yeah. Yes.
And if we keep it like this, also doesn't make sense. 1 should be okay. So heapify is like it sorts the structure.
number heads to the top.
Okay, 8, 3, 5, 1, 2, 9.
We're back to having a max heap. Let's swap the largest number 8 with the item at the end of the unsorted part of the array, 2. We remove 8 and consider it sorted.
Okay, we remove 8.
Again, we need our heap back, so let's call heapify.
Okay, what's gonna happen if we call heapify? This should be here, and 5 should be.
I think 5
will move. 5 goes to the roots.
To the roots,
will go down.
Yeah, 2 and 5 will be swapped.
2 and 5.
Yeah, will be swapped.
Oh.
Then it becomes a max heap.
Yes, I think but it's exactly.
Yeah, this is gonna be. Okay, try.
I think you see the pattern. I'll let you watch the rest of the video without voiceover.
Please mute your mic, Olayudi. Okay, wait. I missed this. So it was 5. Okay,
again,
5.
We need our heap back, so let's call heapify. Pattern. I'll let you watch the rest of the video without voiceover.
Okay, he switch again the last one with the root. Or like he popped the last one, then the root. The roots become 1, 3, 2. Now 3 gonna be the root. 3, 1, 2.
This is heap sort, right?
Yeah, it's heap sort, but he's using the max heap for the heapify structure algorithm.
So it's gonna be 1, 2, 3, 5, 8, 9. Okay.
We're all done. Our array is fully sorted. Here's the pseudocode for heap sort.
Okay. Let me paste it in the chat. Someone wanna go to it. Let's jump to the last video and then we start analyzing the lead code problem. So now we see heap. We have idea about heap. We know kind of how heap work behind scene. Now we're gonna jump to this model Python heapq just to give us like how we can use it. If you wanna like go in details on heapq, you can check this link. But this video gonna give us like basic like enough thing to solve the lead code problem using the heap. Okay, let's go.
Hey there. Heap queue or priority queue is a data structure that is used quite a bit in FANG or large tech company software interviews. The benefit that Python's heap queue provides is that it allows you to maintain your minimum element as your first element of the array at all times. Let's walk through some examples and it becomes a lot more clear. So you import the heap queue module and you can use a list as the data structure that you perform operations on. Now,
can you see the video clearly?
Yes.
Okay, good.
Now, instead of using...
Can you zoom a bit?
Yes, okay. Is this better?
Yeah.
append or pop, you use the equivalent methods that the heap queue module provides. So heap push is the same as append, and heap pop is the same as the normal list pop. The difference is that when you use these heap queue methods, at any given time, your first element is going to be the minimum element. So here I'm
at the first element gonna be the minimum element. Okay, so this is main heap. Okay, main heap. That means the first element is the root. So sorry guys, let me finish. Let him finish the explanation.
5, 2, and 9 in a random order, but the first element of the list right now is 2 because 2 is my minimum here, even though I'm adding it in the middle. The same thing is true for pops.
Okay, so he add first 5, then he add 2, and then he add 9. But when he go to the heap and index 0, it was 2. So like this heap queue it take care of sorting without you care about it. Like if you push any elements, it's gonna be sorted automatically inside the heap.
I think the base of the heap is a mean heap. So however you put it, the minimum will be the root.
Yes, but by the way, in Python there is no max heap. So if you need to use this heap queue as a max heap, you will have one of the trick they do is they convert this value to negative. So if you have -5, -2, -9, then the root is gonna be
so the
-9, and when you pop it, you add minus, so it becomes positive. Because there is no max heap in this module. So that's one of the tricks you use.
I'm here, even though I'm adding it in the middle. The same thing is true for pop. So pop will always remove that first element and returns it. So here 2 is returned. If I do it again, so the next smallest element is 5. So 5 is returned. And if I try to add a bunch more elements down here in, again, random order, so 10, 1, and 3, right now 1 is the smallest one that I have. So if I pop the element, 1 is returned, and the next one in order would be 3. One thing to note is that your list is not, or your priority queue is not sorted. So you're guaranteed that your first element is the smallest one, but there's no guarantee about the rest of them. So we don't know if the index 1 is going to be the next smallest one. When you do the heap pop, a shuffle happens behind the scene, and the next element that you will access, basically the element that gets moved to the first index, becomes the next smallest. But just know that the first one is the smallest. The rest of the elements, we don't know what the order is.
Okay, so when we push element, it doesn't sort them until we try to pop. When we pop, then it's gonna give us the root, and then it's sorted. Okay, that's good to know.
If you're interested in knowing how this happens behind the scenes, you can read more about binary trees and insertion and deletion from a binary tree. In the last example, we started from an empty list and then added elements to it. But we can also start from an existing list and then use the heapify method to basically convert that list into a min heap. So here, after I convert this list, now my first element is going to be the smallest one, which is 2.
Okay, so this is a heapify that we saw in the last video. We have it 529 and it's give us 2. So the root is because this is min heap. In the other video, I think we were working with the max heap, so the root was always the biggest number.
2 in this case. There are 2 other methods that HeapQ provides. One is push pop, the other one is replace, which is the same as saying pop push. And remember, order matters, and each of these just combines a push and a pop operation. So the first one, I am pushing 1 into the heap and then popping the smallest one. So if I push 1 into this list of numbers, 1 becomes the smallest one, and 1 is also removed. So it's basically as if nothing happened. Now, if I do the same thing with heap replace, first the smallest element is removed, which is 2, and then 1 is pushed in. So 2 is removed.
Okay, so this one push, then it will pop. This one push, no, this one pop the element, then it's pushed the new. Okay, heap replace, heap push, pop.
And then if I take a look at my list, I have 1, 5, and 9. And the reason that these 2 methods are provided is that they run faster behind the scenes. Otherwise, they do exactly the same thing as it would happen if you just do 2 separate operations. So the reason that we use a priority queue instead of a list and then continuously sorting it is just time complexity. Sorting a list will cost n log of n, depends on your sorting algorithm, but n log of n is a pretty good estimate. But adding or removing elements from a priority queue costs log of n. So if I were to just add and remove elements from a list and I didn't care about minimum or maximum, then using a list would be a lot more efficient because that costs O of 1. But if I need to know what's the minimum at any given time, then this cost of log of n is the best I can do as far as we know. If I were to use a list and sort it, every time this sort would cost n log of n, and every pop, so here like I've added 2, 1 is still my smallest element, but if I at any point I pop that 1, then I don't have a way of knowing where is my smallest element until I sort the list again, so I know, the leftmost element is the smallest one. So n log of n times however many times we push and pop would be the time complexity. Python doesn't offer a separate module for a max heap. So far we have been looking at a data structure that always maintains the minimum element as the first one. We can just do a little bit of manual work to change that into a max heap, basically keeping the maximum element as the first element of the queue. And I think the best way to go about it is to just multiply everything by a negative. If the list that I'm interested has 1, 5, and 2, basically I'm adding 1, 5, and 2, but I put a negative sign behind them, so I have -1, -5, -2, and when I try to pop an element, I also add a negative sign behind that. So if I run this, the maximum element is popped out of that list, and if I try to pop the next one, and again put a negative sign behind it, the next one should be 2. You can also use a priority queue on objects like tuples or anything that's sortable. Here I have a list of tuples that has the age and names of some people, and this is unsorted for now. I use the heapify method to convert that into a priority queue. The smallest age that I have here is 22, so that is popped out first. But then after that, I have 2 people who are of age 30. Because that first element is equal for both of these, the second one is taken into consideration. And if I were to sort those strings, Ali starts with an A, Bill starts with a B, so Ali would be basically the smaller element overall. So if I try to pop something out, Ali's popped out first, and then it would be Bill and then John.
Okay, wait, let me repeat this one.
Where to sort those strings, Ali starts with an A, Bill starts with a B, so Ali would be basically the smaller element overall. So
wait, so because this have 2 value, it's compared to the character. I think it. Okay, let me repeat this section.
And this is unsorted for now. I use the heapify method to.
So now there is each name and have priority. So this is priorities 45, 30, 22, 30. But this one have same value. So heapify need a way to know how to convert this one or like order them.
To convert that into a priority queue. The smallest age that I have here is 22, so that is popped out first. But then after that, I have 2 people who are of age 30. Because that first element is equal for both of these, the second one is taken into consideration.
Okay, so because this is equal, the second one is gonna be the main comparison element. But this is a string. Is this gonna compare like each character?
And if I were to sort those strings, Ali starts with an A, Bill starts with a B, so Ali would be basically the smaller element overall.
Okay.
So if I try to pop something out, Ali's popped out first, and then it would be Bill and then John. And instead of calling methods on the heap queue directly, you can also just import the methods that you need. So instead of importing the whole module, I can do from heap queue import heapify, and in this case I'm also using heap pop. That way I can remove this heap queue dots and directly call the methods that I've imported. So this has exactly the same behavior, it's just that my code is now a little bit more concise and cleaner. Heap queue is one of the interviewer's most favorite data structures. Try to see if you can solve the question that I've included for you in the description section. See you soon.
Thank you, sir. What questions are?
Thank you, Sabo. He made us feel very lazy. The codes are very, very fast. Like he does everything behind the scene already. So
yeah,
it's taken care of. Yeah.
Yeah, but like I guess in interview you don't wanna do everything from scratch, right? If you're using Python, like in JavaScript there is no something like this. I don't know, maybe if you're allowed to use some module, maybe you can do that. In Python there is this one. Okay, so this is the one that he recommend to solve. Let's see if we still have time, we can try to solve it. But let's jump to this main one that we have. So what is it? This one and this one. Now before we do that, let's read this again, see if we actually understand this, because before I watch video I had no idea. So mention of k. if you see a top of or lowest key being mentioned in the question, it's usually a sign that a heap can be used to solve the problem. If you require the top key element, use a main heap of size k. Iterate through each element, push it into the heap for Python heap queue, invert the value. Okay, invert the value. Now we know what it means, because in Python in heap queue there's no max heap, so we are forced to use the main heap, right? But we are looking for top key element, which means in the root it should be the most great number, right? So we're gonna invert the value before pushing to find the max. Whenever the heap size exceed the k, remove the minimum element that will guarantee that you have the k largest element. Okay, let's jump to this merge key sorting list and we try to do it with the heap. Okay, let me close this. I post them in chat. And this one. Okay. No. This one. Yeah, this one. So, let's see. Okay, don't be scared from this hard. We can do it, guys. Stay positive. Okay, so you are given an array of key linked list. Each linked list is sorted in ascending order. Merge all linked lists into one sorted linked list and return it. You are given an array. Okay, this array of key linked list. In this case, we have 3. So our key is 3 linked list. Each linked list is sorted in ascending order. Okay, 1, 4, 5, 1, 3, 4, 2, 6. Merge all linked lists into one sorted linked list and return it. So we should return this. The linked lists are 1, 4, 5, 1, 3, 4. Merge them into one start. 1, 1, 2, 3, 4, 4, 5, 6. Okay, so we can use heap, main heap, because the root is 1. Because we are sorting ascending, we can use main heap. Okay, let's see how we can now use main heap. Let me screenshot this. Let's go to here. Let's see. Okay, now let's present this in a way that we can understand it. Let's say we have linked list here and we have 1. We have 1, this one, the head of this linked list. 2. We have another one and we have 2, and this one is connected to 6, this one connected to 3, this one connected to 4. 1 connected to 4 here, and this one connected to 5. Okay, and we should return this one, and we should return 1, 1, 1, 2, okay, 3, 4, 4, 5, 6. So this is what we should return. So we're gonna return a new list. How we can use this with the main heap?
Why can't we use the approach the guy used in the last video we watched? Is it not possible to use that approach?
Yes. He did use min heap, right? We can use min heap.
Yeah,
I think
it's min heap. Yeah.
Yeah.
That was what he did. So at the end of the day, when you are popping out, you are popping out the smallest.
Okay.
So when you are popping, you just add it to a list and return the list. That's it.
Okay, yeah. So we're gonna create. Let's say we create a heap. So this is our heap. And it's an empty list, right? And then we should pop this. So we can maybe we do a tree representation. Because okay, so we're gonna pop this and this, or like no, we're gonna add this to the heap. So we're gonna have 1, 1, 2. Now
yes,
we need to, we're now gonna pop it. We're gonna add this to the heap. Now let me remove this. It's gonna be like this. Then we need to sort it. Now we're gonna pop this. Let's pop it. Which gonna become. Wait, there is background music. Check if there is a button there. Oh, it's coming from other tab. Okay, let me pause it. Okay, let me share full screen. Wait, this whole time you guys listen to the background music? Do you see my screen now? So we said we're gonna add this to a heap. Then we're gonna pop this one. When we're gonna pop that one, that means it's gonna become 1, 2. And when we are popping this one, we can add this one. Gonna add this one. So we did pop this one. Now we're gonna move to this one. We're gonna add it, and this, the one that we pop, it's gonna become here 1. Now we're gonna add this one 4, which gonna become 4. How it's gonna be in the heap? It's gonna become 1, 2, 4. 1, 2, 4. Right, and the next loop again, we're gonna pop. We're gonna pop this one, right? We pop it. It's gonna come here. Right, which one is this one? This one, right? This second one. So it's gonna go to this because we pop it. We're gonna also add it next children. So this one is done. This one is done. Next children. So this, when we pop it, it's gonna become 2, 4. And we're gonna push in the heap. The next of this is gonna become 3 here, 3. Next of one is 3. So it's gonna be 2. Like it's gonna be 2, 3,
2, 3, 4.
Okay. Okay. So there is a loop going on here. Can create a loop from this. Okay, now we're gonna go to the next loop. We start again with 2, 3, 4. 2, 3, 4. Now we're gonna pop the root element. We're gonna put it here too, right? And because we pop it, it's gonna become 3, 4. Now when we pop it also, we can reach to, which is this 2, which means 6. So we're gonna add this next of it here. Gonna add it. It's gonna become 6. It's gonna become 2, 4, 6. Two, 4, 6.
I thought it's 3.
Oh, we did pop it. Oh, sorry, 3.
Yeah,
3,
3, 4, 6. Yeah.
Yeah, maybe 3. 3, 4, 6. Okay, now we did that. It's gonna jump to the next loop where we're gonna pop the 3, 4, 6. We're gonna pop it, which means we take it away, we put it here. Okay, notice there's a pattern here, 1, 1, 2, 3. So this algorithm is working. So we pop this and we move to the next, and we keep moving on each list, and the heap is itself doing the magic of ordering. We're not ordering anything, we're just pushing, popping, pushing, popping. So when we pop 3, it's gonna become 4, 6, and when we gonna, because we pop this, so we know what next element it is. It's me. So 1, 2. So we did this one. We pop it. It's done. Because we pop this 3, we can reach to the next element, which is this one, and we're gonna add it. Now 4. If I'm gonna add it with this, gonna be 3, 4, 6. So this is the key. When I push this element to the heap, it automatically gets sorted. Right? I had just 4, 6. When I add 3, it's become like this.
That should be 4. I thought that should be 4, 4, 6 or something. You've already popped 3 already. Yeah, that should be 4, 4, 6. You added 3 already.
Oh, sorry. Yeah. Okay, you're right. 4 here. So when we pop 3, it's gonna add 4. Wait, 4, 4, 6. Okay, so it's gonna be 4, 6. Okay. Let's see how what's gonna happen. Now we go to the next. We can make this maybe shorter. Okay, we go to the next. We're gonna do again 4, 4, 6. We're gonna pop this. It's gonna become here 4, and we're gonna pop it from here. Pop it from here. We're gonna push at next element 5. Right? So if here it's become 4, 6. It's become 4, 6. Now when we gonna add 5, because we pop 4, it's gonna become 4, 5, 6, 4.
Yeah, 4, 5, 6.
5, 6. Okay, now again we're gonna pop 4, next loop 4, 5, 6, pop 4, gonna stay 5, 6. Let's me add 4 here. right? Still have 5 6, and this 4 I did pop is this one, so this one is done. I'm gonna push it next element. It doesn't have.
The list is empty.
Yeah.
It's all empty.
Yeah, it doesn't have. So what's gonna happen here? Nothing. It's gonna stay 5 6. Right? Let's see. Push this a bit. Nothing gonna happen here. It's still 5 6. Let's go to the next line. We have 5 6, and in this part we pop. We're gonna pop 5. Here's pop 5. I did pop 5. Now I need to add it to the, of course, it's gonna be 5 here. Okay, and when we pop, what we do, we push, and this one doesn't have anything to push, so it's gonna be just 6 here, and there's nothing to push. Right, let loop again. Let loop and see what's gonna happen. So next loop we have 6 6. I'm gonna pop it, and when pop it I add it here. 6. I go check to push next element of 6. It doesn't have. It's null. So there's nothing to push, and my heap is 0. It's empty. So I can do a while loop here, like a while loop on the heap. As long as the heap is have some elements, I can keep looping, and we can follow the same algorithm. We pop. So first we add the head of each linked list, and then we build this algorithm that keep looping. Just looping, pop this, add next element, pop this, add next element. Now we need to write pseudocode. What do you think, guys, about this algorithm? I think it did solve the problem. Maybe it's not the best one. We can see later if there's better than this one. So how we do pseudocode? First we can write pseudocode directly here. This one. With this. Okay. Where is the code? There. Come on. Okay. So we know it's how it works. Now we just need to convert it to a pseudocode. So if it is how we need a heap, right? Heap, and so add the head of all linked list to the heap, right? Then what? So we add this and this and this. Then it give us this heap right here. It did give us this heap. So now in my heap I have this, right? Now when I have this, I need to pop. So pop pop heap pop. I'll just say pop elements from heap. Okay, what I'm gonna do with this when I pop it? So the goal is to create a linked list, right?
Yeah, so you're gonna add it to a list, no?
So maybe here we create
sorry, can I ask a question?
Yes, go ahead, please. Can you repeat?
You know, we're using a linked list, so that means you have to, how do you call it? You have to, is it break the list? I don't know. You have to rearrange the list. We are using 3 different linked lists. So we'll have to like move the head, then adding other to it to form another link.
Oh, okay. I see what you're saying. You're saying like instead of like creating a new list, we can just converting, like connecting this to this.
What I'm trying to get is, if you are going to, since it's a linked list, it has a head, then is connected next. So that means you have to do all those operations of breaking the link list for each of them.
Oh, what do you mean breaking the list?
That's what I don't know how I can explain. So,
You
for
mean
example,
rearrange the pointers?
You mean splitting it?
Yes, like changing the pointers. Yes, like splitting the link.
Oh.
So that you can get each node. Is that how it will go?
I think in Python, the way they are represented is like a list of lists. So every list, start from list 0, list 1, list 2. So everything is all connected by.
Yeah, to have next.
They are nexted to each other. Yes, something like a nexted. Yes.
Okay.
So like because when we're gonna pop this element, we can reach to it next, so we can know which one is connected to it.
Oh, okay. It's not like we're breaking it. Okay.
So any node you are in, you can reach to their next, and it's it's gonna take you to the one that connected to it.
I'm still thinking in C. That's why.
From my brother.
So how we said we're gonna create, because what the goal of popping is to add it to this linked list, new linked list. So create empty linked list, create empty linked lists, add the head of all linked lists to the heap, pop element from the heap, add it to linked list, to new linked list. Okay, we pop one, we add it to the new linked list. Now in our linked list we have this one. Then our heap automatically in the background gonna be like this. Now we need to add this element, the next of the one that we add to the new list. So we can do push element next to the heap, the one we pop. So element next to the heap, it's gonna become like this. What's next? Okay, we push it. What we do? We go to the next one, to this line. So this is another loop. Okay, when we push it, that means the heap is gonna sort it itself. So if I loop here, if I create a loop here, is this gonna give us the same concept to create? So let's say we're looping. Okay, I'm here. I did pop elements from the heap. Okay, that's what we're doing. Add it to the new linked list. Okay, it's added here. Push element next to the heap. Okay, that's what we did here. We push it to the next, and then we're gonna loop again. Okay, it's gonna pop it again. So this piece of the code describe what's happening here, I believe.
I think so.
But now the code is the The code is where you have to try to do
Are you
it.
using that heap queue?
Yeah, so I think it
That's the best. That's the best one to use.
yeah,
AQ.
import heap queue. Okay. Now we create a linked list, empty linked list. So let's call it maybe a result, or just results, or new link list, list node. Okay, let's create a new linked list. Where is it? Add the head of all linked lists to the heap. Okay, we create the heap, and okay, this is our heap. Now how are we gonna add all the linked lists to this heap? We use push, what is called? Push,
Heap push?
heap push, yes. Okay, heap push, this one. So heap, but wait, how are we gonna do it? How are we gonna get this? Let's see because we wanna push all the head of the linked list. So we wanna push 1, 2. How are we gonna do it? Loop?
Yeah, loop, I was thinking.
So like 4 maybe head in the length of this.
Yes, for each head in the link list, right? I think something like that.
In the lists, yeah.
Oh, in the lists. Okay. Okay, so for each.
So this head now, this head, is it getting the one element in each link list, or is getting the full? Because looking at it, it's like we have,
Okay.
we need to be sure what it's getting. Is it getting the complete list, or just one element?
Okay, so it's gonna get the list, but behind the scene they are connected to it. So let's do print head. That's value. That's value. That's val. So this should print 1, 1, 2, right? Let's see.
Exactly what I'm curious to know. Yeah.
1, 1, 2. Because this is obj, and it's connected to. So like if I print head here, you're gonna notice it's connected to. The other nodes are connected through it. You see, list node 4, 6, but this is the first one. Does it make sense? So this element is list node, and inside it there's another list node, and this one another list node inside this one.
It's like a Russian doll.
So I saw someone in chat write head 0. I also touched that, but when I printed it showed me that it not like that. So now we have head. Okay, so
yeah, it's important to remember it's not an array, that list. It's it's an object.
So how are we gonna do this? Push. Okay, we say push. Okay, heap push. So heap q dot heap push. Now you give it the heap. Our heap name is heap, and what you give it? You give it the value. But in our case, we don't have just value. We have. So we need to. So our priority is gonna be the value of the node. So let's say we're gonna create a tuple. because we need to pass. Okay, let's go back to there. When we do here, when we do pop, we put it here, right? We put it here, but notice we need to add its next element. So somehow in our heap, we need to save the node itself, the next element that we're gonna, that's connected to this, I think.
But if the head is if the head still has connection to the next element, I think you can still add the head value. Okay, no, it's just the value you're adding. You're not adding the node.
Oh, that's a good idea.
So you have
So
to add
we
the
can
node.
do just a value, but in that case, we are sorting just the value. We need to, because the goal is to create a node at end. So we need to pass also the node itself, right? So when so because this we're gonna need it later when we're gonna what's it called, when we're gonna push this to the linked list. No, sorry, when we're gonna pop, no, when we're gonna push, yeah, because when we pop this, we put it in the linked list, right? And then we move to the next. Now, how we can move to the next if we don't have this node? If we push just the value is just a value, it doesn't have anything. But if it has the second element that is the object, I can do head next.
Yes.
Can access head next. Okay, but here we're gonna find a problem. If you remember in the video, if the first priority is the same value, the heap move to the next element to compare, right? So let's say we have two same value, for example this 4 and 4, they have same value. So when it's gonna be doing the comparison here, it's not gonna know which one is gonna put in the top, because they have same value. So it's gonna move to the next element, which is head. But head is an object, it can't compare it. So I did check this before, and the solution was to use index, for example index. But here we can't use index. Maybe you can do it like this. Is this gonna give us index?
I think it might.
Or we do for range for head. How we can get index here? So basically my point is we need another element here that will be able to compare if it was have the same value, which is index. Index is a value that you can compare. Now here we need to get indexed. I'm not sure how in list can get index, but I know if we did like 4.
Yeah, let's try 4.
So for E in length, or like range of length list. So this is gonna give us index, which is gonna be nice. We can use it here, but we need to change. So because we are using E, so this is gonna be list E, and this is list E. So this is our array here, right? So this is our array. Now this is the list index 0, index 1, index 2, and we said in here add the head of all linked list to the heap. So I'm gonna loop on index 0, then I'm gonna increment it to index 1, 2. So to reach the value of this linked list, I need to do list E, which is 0 in this case, first one, and then it's gonna be dot val, and this gonna be 0 first one, and this gonna be the whole list.
Sorry, can you try printing the list 0.val? And I'm sorry to take you back a bit. I understand what you're doing.
No,
Anyways,
please be free.
no, I understand what you're doing, but
okay, let me comment this.
Just print just comment, yes, print the list 0 of .val. Let's just see what comes out.
Okay, do I print them all, let it loop over them, or I print only index 0?
Just 0, just put 0 inside
okay.
the index. No, 0 within the index.
Let's do index 0, so it's become more clear. List 0. So the second one gonna print everything, all head.
Yeah. I get your point. Nice.
So this one gonna run. Okay, what did I print here? Oh, I print list E, list val, right?
Yes, .val, yes. So you forgot to put that part. .val, yes.
Okay, so index 0, 1, index 0, 1, index 0, 1. But the first head was 1, the second head was 1, the third one was 2.
Then 2. Nice.
Which is
nice,
1,
yeah.
1, 2. Okay, so we can. So what this gonna do is it's gonna add the head of all linked lists to the heap. Heap. Oh, heap. Oh yes, it has here heap. So heap, the function heap push. Where I'm gonna push in my list heap. What I'm gonna push a tuple. What's inside this tuple? There's 3 elements. The first element is the priority, which my list gonna be sorted, which means the value of the linked list. So list E val, and I'm gonna add the second element, which is index, randomly, just in case that 2 elements have the same value. So the index is gonna be, because they can't have the same index.
Do you need is the last one necessary? The last
yes
one you're using for the that one is necessary.
Yes, because at some point here, if you notice, when we pop element, we add it to the list, right? When we pop it, from where we get it? We get it from the heap, right?
Yeah.
So at some point, the element that we pop, we need to do next of it to push it to the heap. So we need at some point to do heap q, heap push the element we pop, next element we pop, that next, right?
Yeah.
So the element we pop, we need to add it next here. So when we are popping, we need to pop this element. Let's see. It's not clear so far. But let's say we add the node list here. If we didn't use it, we can remove it. So.
Because what I was thinking was maybe you need to push everything first. Then when you're done pushing, you can now pop them one by one. I don't know. That's what I was thinking.
I was also thinking something like that. Since the heap will sort itself out, we could just go through everything once, adding it, and then go through it again just to pop it, and then you know what I mean, reheapify it, and then pop will do that automatically, of course.
Exactly.
Look at us having a time complexity of n squared.
It seems it won't be n squared per se, because we're going through the loop. It's 2 separate loops. It's not it's not a, what do you call it? An embedded loop. So it's not n times n, it's n plus n.
Okay, so your Yes, go ahead.
Because it's a list of lists, you understand? It's a list of lists. So it means that we have to iterate inside each of the lists. Yeah. It's almost like n square, but it might not
It's a
necessarily be
list
n
of
square.
linked lists.
Yeah, it's
Take it.
but we only have to
A
go
list
through
of linked lists,
each
not
one
a list
once.
of
Yes.
lists.
Yeah.
So we go
Okay.
through every element. That will be n times, right? For the number of elements to add it to the heap, and then the heap does its thing, of course, with the n log n to put them in the right position. And then next time we go through the list again, or the heap in this particular case, it's to extract them and then to put them properly into the list node format, and then we return the list node. So those loops are not embedded, and we're not necessarily going through, you know what I mean? I don't know, but regardless, you have to go through each element at least once to, I think.
Okay, just to like follow. So we're gonna add this to the heap, like add this, add like everything,
Yes.
and then
Well, there's no
gonna-
way. Sorry, there's no way we can do like what the guy was asking. There's no way we can achieve using one loop to do the both operations at the same time. It's not. I don't think that will be possible. So we just have to do it on separate loops.
Okay,
Yeah,
we
but they
can-
won't be embedded, so the complexity won't be too great, no?
Exactly.
Okay.
So your intuition was right, Nux. What we're suggesting is that perhaps we have one loop that pushes everything into our heap, and then we have another loop, since the heap will now be in its min format, because heap q, right, we'll put it into a min heap, and then after that we pop them to put them into the list node in another loop. That way we can assure that it's ordered. Is my suggestion, but
okay, we can code this one, and then we try that one. See.
yeah, because if we want to take advantage of the heap, we need to put it in the heap format.
You mean like
Sorry,
this?
Musif, can you just do this and print the heap? Let's see what's inside. Is it possible?
Like print this?
And like run it, then let's print. Yeah, after the loop
Okay.
done,
You
let's see
mean
what's
when you
inside
finish the code?
Yes, yeah.
Okay.
When we finish, no, just this part. When it's done, pushing it, let's see what's inside the heap.
Okay, so
Is it possible? Yeah.
yes. So now which parts we are? Add the head of linked list. Okay, so this part is gonna add all the head to the linked list. Now we're gonna loop, right? Okay, you said let's print the heap. Let's see what's inside. Heap, print heap, run. So it have 1, 0, the linked list, then it have 1, index 1, the linked list, and then it have 2, index 2, the linked list. So that's what we have in our heap, which means if you notice, it's the same one we had, this one, 1, 1, 2.
Yeah.
Now, let's have some error here. Has no attribute val. Which one? Non-type object has no attribute val. What that mean? Oh, maybe I did. Maybe -1. Okay, so maybe it was the length is bigger. Okay, so now we're gonna create this main loop that's gonna go through all this tree. So it's gonna be while we have something in the queue, because we wanted to stop here when there's not. While heap. what we're gonna do, pop elements from heap. Okay, in the heap we have a tuple, right? So we have what this called value, val. We have index, and we have the node equal pop. So it's gonna be heap q heap pop and our heap. Okay, so this gonna pop the lower element 1. Okay, what we're gonna do when we pop it? Now we have the value here, we have e, we have node. Now we said we create a new node, so let's create a new node. We have new link. We're gonna create new node. How are we gonna add this value to this new link?
That was what I was trying to phantom, because that's what I was trying to ask you, because what the result was, the output, it's like one. I don't know whether it's just a single list.
So
that's what I don't know.
Okay, so there's a way. We did create this new link, right?
Do you explain that line 22?
Line 22?
Yes.
Okay, so this is a tuple. This tuple have like three value. So it is a tuple like this. It have value 1, 2, 3. In Python you can unpack this 3 value in 3 variable just by doing the first variable, second variable, third variable. When you do this, it's gonna take this, save it here, take this, save it here, take this, save it here. And because we are the one that create this tuple, we already know what's inside each index. So we know the value is index 0, 1 is the value is index 0, index is 1, and the node is 2. Now we create this. So this is like a dummy node, right? So this is just like a dummy node. So the new linked list it's gonna be like this. This is what that we create, right? Empty, just a dummy node. Now the next of it is gonna be 1. So it's gonna be list node and the value. So this gonna create dummy node that we have already, and the value which is 1. Is it clear? Now,
so what is the popped value like? What's the result of the popped value? Okay, actually tuple, right?
Is 1. When we pop 1, we get this pop.
Okay, when you pop, you get 1 first. That's it.
No, here when you pop you get the root element.
Exactly. So I'm asking, the root element is the tuple that you created initially, right? That's the one you pushed in.
Yeah. So yeah. So I did, when I pushed them randomly, like just looping, pushing 1, 1, 2. But when you do pop, it sort them, then it give you the most list element.
Yeah, I get.
And now we did create this linked list. We add it to the linked list. Now it have here, right? Now add to the new linked list is done. Now we need to push the element to the heap. Okay, how are we gonna do this? How are we gonna push the element to the heap? So because we need to push the next element, which is 4, right? We need to push the next element to the heap. Okay, this is new linked list. Okay, let's write how it's gonna push. It's gonna be like heap q heap push. We're gonna push it to the heap, right? Now we're gonna push 3 tuples. So okay, so this one we know it's gonna be index, and this one we know it's gonna be list E. No, not list E. So here, how we can get this new link? Next. So wait, bit confused. Maybe we need a pointer. New link next. So I did go to this. So this is new link, right? I did go to new link list. I added this. I need to move this pointer to here. So the new link. So maybe this should be. Maybe you should create pointer current and give it like new link, and here we do current next. So this is like a pointer. Now our current gonna be equal current next, which is this one. So this current is here. Now we can do maybe current.
Sorry, if you're doing it that way, why do you have to use next in number 24? That should be current now. That's the first one. Then we move next. Then we update it again. I don't know.
Wait, can you repeat, please?
I mean number 24. Line 24. I was thinking it's supposed to be current, but you need to start from somewhere, then you move next for the next linking. You can correct me if I'm wrong, but that's how I see. That's the way I see it. I don't know if I'm correct. The way I see it that way.
Maybe I'm confused. I'm still like trying to also understand.
Okay.
So we have a new link, right? We create a new link right here. Then we put a pointer on its current, right? You with me? Now, when we pop this element,
yes.
We said, okay, this is the next of the current. I want you to create a new node with new value here, 1, right? Now the current next become connected to this new value, right?
Yes, I get.
Now we need to, this one is have 4 and 5. Now we need to reach this 4. Wait, we have node here. Wait, what I'm doing? We have node here. See? So we can do node next. Because we wanna push the next node to the heap, and we have node. So if I push node dot next, it's gonna work, right? Okay, it's a bit confusing, but we can go.
That's why I told you. That's why I told you to print the value of the popped, so we know what's coming out from there. But
yeah,
it's okay.
We did. It's here.
This is the popped. Oh, I didn't know you printed the popped. So sorry.
Oh, the heap. So the this is we print is the heap, but it's the same. It's gonna pop. It's just gonna be 1. So it's gonna be this part. It's gonna be 1, 0, and the list. Let me try print it. Wait. Wait, what's happened? Okay, print. No, I think I click. Okay, so this is our value.
Can you just print the 3 of them? Yes, nice. Print 3 of them.
Or let's print this like this. To remove this?
Yeah. No. Oh, okay.
So what does it give us? It give us 1 0 1 0. I don't know what that means. Oh, because there's 2. There's 2 1. Okay, wait. If I did like this, run, because there is 2 have 1 1. I'm confused. Print value 1 0.
I think the I is the index now. That's why you're having 2 1 1 there.
Why does it print? Why does this one print 2? Let me do like this. Run. Okay. So this one gave 2. Confused. So it's return this and this. Oh, my bad. Because we are in while loop. Oh my god. So it's running twice. Okay, so let's remove the while loop. Run. I'm like, why is give 2? Of course it's gonna give 2. Index out of range. Which one? The heap.
The I. What is I? Okay, okay, the pops. Yeah.
Okay, why is index out of range? Heap. Index out of range. What does that mean? Heap. Oh, okay, so if heap do this. Run. Okay, so now it's printed one time. So it give you the value, and in the index, and in the node. So the value is 1, right here, and the 0 because this is index 0 in this list, and the node which is itself. Is this clear?
All right, it's clear. It's clear, very clear now. Very, very clear. Thank you. Thanks.
Okay, so while app, and okay, I forgot to say what was before. But
So you can make use of the node since it's actually going to take you to the next the same node over there.
Okay, so we said this current next is gonna connect this, and we had one problem is how to push, how to add this element to the heap, but we figured out that we have node here, we can use it to push the element. So how we're gonna do this is heap q heap push, and so the first one should be a value that prioritize. So we can do node next value, right? So if you notice, we add 4 here, right? 4. That was here 4. So node dot next, it's gonna give you this. Now we are in next, which is 4. But how we can reach the value 4 is that val. So yeah, someone said something. Heap.
I think it should be node dot value, not node dot next dot value.
Node. Can you repeat that?
I think it should be node dot value,
Node dot
not
value.
node. But yeah, because since we are already in, we have not yet entered the node. So yeah, this node is like is, how will I put it? We have not yet entered the node, so we should just get the value of the node. Then we can now next it to the next one.
Yeah, but in here we put the whole node. If you notice here, we put the whole node from the one.
Oh,
Maybe
okay,
if we
okay,
did
okay.
here next,
Yeah,
then
you can continue. It's correct. Yes, I've seen it.
yeah.
Yeah, it's okay.
So maybe
You
we should
can,
do next here.
No, leave it the way it was.
Okay, so we push now. Let me repeat just in case someone confused trying to catch up. So we said we loop through this heap, right? We did loop right here. We add them all to our heap. Now our heap have this 3 value, right? 1, 1, 2, right? Now we go to the next element, which is a loop that's gonna keep looping until the heap is empty. That's why we did the while loop. Now we have this dummy node empty that we create here. We call it new link. Let's call it dummy, right? And then we said we create a pointer current, and we put current that points on this dummy, right? And then because we're gonna need this to merge or add to this linked list. Now we did heap pop. Now what happened? We did pop this element, right? Now when we're trying to explain this algorithm, we said when we pop it, we need to add it to the linked list. Okay, that's what we're trying to do. We create to add to the next of this dummy node, we need to next of it to append to it, or like to add. So that is current that next, and then we create a new node, and the value of it is the value of 1. And because we pass the value here when we create it in the heap, we can easily retrieve it from val. Now the main part is done, but in same time, when we add it to the linked list, we should add its children or the next element to the heap so it can get sorted, which this line does here. Heap push heap. You're gonna push elements in the heap. What element you're gonna push? The node, because when we retrieve this pop it from here, we have the node, so we have access to that element 4. And then E, because we have access to E here. And now here we did node. Now we can do node next. We pass in third argument node. So node next is the one that we're gonna pass with this. It's the one that's gonna be added here 4. Okay.
So I think before.
Right, so if our code is correctly, then we should return the linked list, right? Return the linked list, which is the dummy, but we don't want this part empty. Our linked list starts from 1, so dummy next, because I wanna my linked list needs to start from here, right? This it's just dummy node. Dummy next. Okay, so wait, we have a problem. What if, because at some point, if you notice here, when we're going, we adding next element, there is null elements null. We don't want it to. We don't want to need null element. So here, if node next
If
exists,
not those next. Yeah.
then add this. We don't want to push to the heap another element because each one it's finished with null. So let's see. Run. Okay, we have one problem. 5. Expected 5. So what the hell happened here? Let's see. So create dummy linked list if not next.
Sorry, I just want to ask a question.
Yes.
I want to ask a question. Please, sorry. Is there a way to just get all the values inside the heap, then use this your method that you are using to also connect back those values through a node like this way you're doing list node to now link all those values one by one. Already in the heap it's sorted. So I'm just asking if that can be possible to do.
I think that's possible. We can look for it, but I found out something here is we don't move the current because when we add this, the current should move to this, right? So when I add something else, I need to move the current to this. So I'd add this line here.
Yeah.
That's why it wasn't. You see, it didn't add anything. Or like it keep adding in the same place. Like it just keep adding the same. Okay, run. Okay, still some other problem here. Okay, now it's adding, but there's some difference. So 1, 1, 2 is not here, 3, 4. Okay, maybe the... So 2 is not here, 3, 4, 4, 5, 6 not here. So this is not here. And 2. Oh, maybe the...
Yeah, the last node is not there. The last layer list.
Maybe this -1?
Yes, I think. But it's going to complain for index range.
Okay, what if I did if? Because I think some of them are not list. Like if list exist. P. If it is a valid list.
Okay, that might work.
Okay, accepted finally.
Nice.
Okay, that's good. Let's see what is okay, 80%. Okay, that's really good. Now
Not
let's
bad.
see. Yeah, can we do it the way like push everything to the
Congratulations.
Good job, guys.
Congratulations.
Nice
Congratulations, boss.
Nice work.
Congrats. Nice.
Nice.
Yeah, please.
Great.
Like review it like step by step again, like the code. So those of us that did not really grab it, we will grab it. Just the code itself.
Okay, so here we import the heap. We create a dummy node, this one, empty one, and we create our heap is a list. And now in this part right here is we're gonna add the head of all linked lists to the heap right here, right? And we're gonna loop on each of them. So 1, 2, 3, we're gonna loop to them. But for some reason here, some of the list is not like a valid list. So we need to check if it is a valid list. Oh, maybe because they are testing an empty list here. Oh, yeah, maybe this. You see, they are testing an empty list. So our code in this case gonna fail because how you gonna push something is empty. Okay, so we know that's what the problem on this. Now in this part we're just adding this element to the heap. So let me show the pseudocode. This part right here. Create empty list, and we add all the head to the heap, right? 2 of them. Now we move this dummy, we give it like a pointer, so we can traverse each time we add new element, and we create a while loop, this one right here. What is gonna do is gonna pop elements from a heap, add it to the new link list, push element next to the heap. So pop when we're gonna add this to the heap here, and then we're gonna pop it, right? We're gonna pop it, we're gonna add it to the linked list here, 1. When we're gonna add it to the linked list, we're gonna add the next element of it to the heap, and so it's gonna get sorted. So when we loop again, we're gonna pop the next element after it gets sorted. This like PLD is recorded, like you can watch recording later when I was like because I see there's a lot of text over here.
That's why I told you to always print it. So that's what made me understand it very well. When you were printing it, I was able to see the values. So that would make sense. If you're writing codes like this, it's always important to print each step, so at least you know what's happening, so you can know how to continue along with the problem you're trying to solve.
Okay, so yeah, so while looping until the heap is empty, we pop the element, we get the value, index, and node itself that we add. Then we create a current next, which mean we're gonna create a new linked list. We're gonna append it. We're gonna append the new value that we get from pop. We're gonna move the current from the previous element to the next one, and if it is not a valid node, which means it's not null, because at some point we're gonna reach to the last element which have next null. We don't wanna add that, and then we're gonna push that element to the heap. We're gonna push the next of these elements. When we pop it, the next of it, we're gonna push it the heap. Okay, now is there a way to do what add alternative solution, which is like add everything to the heap? Like instead of adding just this, we can add everything, and then we can keep popping, right? Is that one that you suggest?
I think this is better because this one has.
This is okay. What I suggested initially was put all the values, every of the values into that heap. Then automatically the heap will have already sorted it. Then we now create a node, and for every node we have to now attach the value and then return it. That's what I said. But it's fine. The approach is also okay as well.
Yeah, but okay. It would be nice to learn how to do it, like how to add everything. We can. Okay, let's think a bit. If we stack, we can ask ChatGPT. So we can.
I'm considering the time. That's why, so we don't stay here for too long.
Oh, okay. 9:20. Oh my God, I lost. I didn't feel time. I swear. Okay, we can stop here. Maybe in the channel general chat, or like in the forum in Discord, someone paste if you find solution to it, because I think that is also a good way. Just add everything and just keep popping like we did here. So this part's gonna change instead of adding just 3. Okay, let's end this session here. Thank you everyone. Next session gonna be about
thank you
tomorrow.
Thank you, boss.
Be about tree.
Thank you.
The tree is also fun. Let's see what it's gonna be about. Okay, have a good night. Thank you everyone. Thank you Nangasi, Pascal.
Good night.
everyone. Thank you guys.
Thank
Thank
you.
you.
Max. See you
Bye.
guys later.
Good night.
Have a good night.